Swayam Prabha. Digital India. Educated India.
Alright, hello everyone, welcome back. So in the last lecture we emphasized why it is necessary to actually go to lower intensities to actually study the quantum properties of light. So this lecture I want to introduce photon statistics, and I'll do this by considering the same example that we were just talking about. So let's say I have 1 nanowatt of power which is incident, and let's say the energy of the photon is 2 eV. So we saw that it will have roughly 3.1 into 10 power 9 photons per second. Okay, photons per second. Let's see. I'll put it. Now we asked this question, how many photons are there in 30 centimeter line segment. So on an average we should have the number of photons in that line segment should be 3.1 photons in a 30 centimeter segment, right? Now the question is, at what position will they occur? Or you can also say, if you are having such a light, at what time instant are the photons detected? What does it mean? Now I have drawn this, let's say this is my 30 centimeter line segment. So I can have a photon here, here and here. That's one possibility. Or it's also equally likely to have a photon here, here and here. There's no difference between the two, right? We have not made any determination of when the photon is going to hit. Okay, but then the photon can come at any time, but eventually we know that the photons are quantized, so the photon number is an integer. What does it mean that photon number is an integer? Well, if you have this line segment and you make a measurement, let's say you take a 30 centimeter line segment, you keep taking a snapshot. Let's say somehow you have the capacity to simply take a picture of the 30 centimeter segment, and you can find out how many photons are there in that segment, and you keep repeating that. Okay, so when we say that there are 3.1 photons in a 30 centimeter segment, we mean that if you keep making this measurement, sometimes you might detect 3 photons, then 5 photons, sometimes 1 photon, and then sometimes even 6 photons, and then 9 photons and 0 photons and so on. You will have various numbers that come up. Okay, so because of the inherent discrete nature of the photon, there is going to be a certain distribution associated with the number of photons. Okay, so basically the time instant is going to be time instant when photon is detected is random. Okay, I can make it even more obvious by considering a shorter time segment of a beam. Instead of 30 centimeters, now consider only 3 centimeters. How many photons will be there in the 3 centimeter segment? Well, the question will be 30 centimeter corresponds to 1 nanosecond. So 3 centimeters will correspond to 100 picoseconds. And if your photon flux is 3.1 into 10 power 9, so a 3 centimeter segment will have an average number of photons of 0.31. What does it mean average number of photons is 0.31? That means you keep again the same thing of taking snapshots. You will make, let's say you make 10 measurements. You will have an output in such a way that 0, 1, 0, 0, 0, 1, 1, 0, 1, 2, 3, 4, 5, 6. This could be the output. So basically if you make this measurement 10 times, on 3 occasions you will find a photon in that line segment, and on 7 occasions you will not find a photon. right? So basically what we are saying is, if you go even further, let's say instead of 100 picoseconds, take 1 picosecond. You are able to somehow look at 1 picosecond intervals and you make measurements. Oh, is a photon there or not there? So if you take 1 picosecond intervals, your average number of photons is going to be even smaller, right? For a 100 picosecond interval, it's 0.01, 0.31. So for 1 picosecond, it should be 0.0031. That's the average number of photons. That means you will have 3 photons that are detected in 1000 pulses or 1000 measurements, right? 3 photons are detected in 1000 measurements. Okay. So what it means, and you have no control or no way of predicting what those 3 instances are. Okay. So basically the conclusion from this is, if you are dealing with short time scales, we are dealing with some kind of fluctuations, random fluctuations. Okay. So we can conclude that at short time scales like 1 picosecond and so on, the discrete nature of the photon gives rise to fluctuations or leads to fluctuations. Okay. What are those fluctuations? How will they look like? Well, to understand that, let's just take a small detour. Okay. Let's consider a perfectly monochromatic wave. Okay. We have dealt with it many times so far. So let's say it has an intensity of exponential E of xt. That's electric field for a monochromatic wave. That will be of the form E naught sine. Okay. Sine kx minus omega t minus plus phi, let's say, something. Okay. And let us assume that it has no fluctuations at all. It's a perfectly, constant intensity. Okay. So basically, no fluctuations in intensity. So this will occur when, if, E naught and phi are constant. When you have no fluctuations, this is true, right? If you even take such a beam, and let's say that beam has a power, P is basically power of the incident beam. So what is the number of photons? We have done this just before this. So flux, number of photons. Photon flux is going to be simply power by h nu. Okay. So, and what is the, let's say if you take a line segment of length L, okay. If I take a line segment of length L, the number of photons in a line, beam segment, not a line segment, beam segment, in a beam segment of length L. This is going to be the flux times length divided by the speed of light. So speed of light second goes up, so that cancels out, so you get the number of photons. Okay. So you have a beam segment of length L and you got the average number of photons, something, n bar. Okay. This is equal to n bar. Now, if you divide that into further number of n segments, okay. So now you basically divide L into n subsegments. What happens? What is the probability of finding a photon in one of those segments? Okay. So probability of finding photon in a particular segment. This is going to be simply the average number of photons is n bar. So n bar divided by the total number of segments, which is n. So that is the probability of finding it, because there is, you cannot predict. It's an intrinsically random process. So one photon has nothing to do with the next photon. So basically the probability is going to be simply average divided by n. That's the probability in finding in a particular segment. And the length of the segment is going to be L by n. Okay. So now we can write out the probability of finding n number of photons in a particular line segment. So in the previous case, we said that, let's say you can have a scenario like this. In a particular segment, you can have 3 or 5 or 1 or 6 and so on. You can have various number of photons that are coming in, right? So what is the probability of finding n number of photons? Probability of finding n number of photons in a particular segment. Okay. That obviously, it actually follows the binomial theorem. So you'll have basically n factorial divided by small n factorial, n minus n factorial into the probability of finding a photon in a particular segment. So let's n photons in a particular segment. So p power n into 1 minus p power n minus n, capital N minus small n. So basically this is the probability of finding a photon, n number of photons. This is the probability of not finding n number of photons. Okay. And then now, there is some algebra that you can do, but essentially if you consider a case where n tends to infinity, you can show that the probability of finding an n number of photons in a particular line segment is going to be dependent on the average number of photons to the power of n exponential minus n average divided by n factorial. Okay. So this is the probability of distribution, distribution that tells you what is the probability of finding n number of photons in a particular line segment or beam segment. And now n is going to be 0, 1, 2 and so on, integer numbers. Okay. And okay, the question is, if your probability of finding a photon is very, very less, 3 photons in 1000 pulses, why do we have to go with that? Why don't we deal with larger number of average, larger segments so that you'll find a photon? No, the question is, we are trying to find the distribution of photons. What we are saying is, if you go back, we are saying that in this particular beam segment, you will have 3 photons. But there is no way for us to tell what is the distribution of photons. Okay. How will you find out the distribution of photons? Because we want to know what is the quantum nature. Quantum nature essentially means you now initially it was a wave and everything was fixed about it, classical fixed amplitude and so on, right? Now when we go to low intensities, now the discrete nature is coming into effect. Just because of the discrete nature itself, we are getting some fluctuations. What are those fluctuations? In a way, you could relate it to the classical uncertainty relation. Delta P times delta X greater than or equal to H cross by 2. What is that telling you? If your X is very, very large, then you don't have any uncertainty. When you come to delta X to be very, very small, then there is this energy uncertainty which gives rise to quantization, right? So similarly here, when your number of photons is very large, nothing much to worry. You don't even need a quantum picture. The classical picture works very well. Okay. If it's only, when you go down to small number of photons, you start seeing the quantum effects. That's a holy grail. So if you want to understand what is the quantum effect, you need to know what is the distribution of photons. Now, how will I know that? By, let's say, essentially sampling, right? If I make large samples, of course I'll get 3 photons. If I take, instead of 30 centimeters, I take 3 meters. If I take 3 meters, I'll get, everything will have average number of, 3 photons or 30 photons per meter, whatever. You get that. You get an integer number, no problem. It's only when you go to the very, very small segments, you will start actually seeing the randomness. You follow? See, let's say this distance of 1 feet has 3 photons. But every time you are measuring, let's say 3 meters, each measurement will have roughly 30. You cannot know the distribution. You will not know the randomness at all. Right? Only when you are actually, let's say, okay, think of it like this. You have a machine which is throwing constant number of balls at you. So what you're doing is, if you want to know what is the distribution of it. Are the balls coming uniformly or non-uniformly? You want to know. If you try to simply put all of the board, open the door, put all of the balls, close it. Okay, if you wait long enough, the same number of balls will come. But only if you open the shutter for a very small time, then you will know whether there is a non-uniformity or there is a distribution in the number of photons or not. So it is essential for us to measure at very, very short time scales. Only then we will study. That's what we are doing. So that is why we took a segment L and we said the average number is n bar. Now I'll subdivide that segment into subsegments. And there is a probability of finding a photon, number of photon, the probability of not finding a photon. So that's why the binomial distribution. And if you take n to be large, mathematically you can show that it ends up with this distribution, which is called as Poisson distribution. Okay. Wherein basically you have two parameters. One is the average number of photons. We'll also want to find out what is the distribution of photons. What is the variance or what is the fluctuation in the number of photons. That's something that we will look at. Okay. So this expression here is what I was saying. This is the Poisson distribution. This is valid when you have completely random events, integer number of photons that you can detect. Let's consider the case where the average number of photons is equal to 1. Okay. So this distribution only has the average number of photons as an input. So now what is the probability of finding 0 number of photons? The average number, you are making a measurement, where the average number of photons in a measurement is basically 1. So if you make a measurement, what is the probability of finding 0 photons? So basically n bar is 1, 0 into exponential minus 1 divided by 1. 0 factorial is 1 anyway, right? So this is 1 over E. Okay. What is the probability of finding 1 photon when you make that measurement? It's simply going to be 1 power 1 e power minus 1 divided by 1. So 1 over E. What is the probability of finding 2 photons? 1 over 2 and e power minus 1 divided by 2 factorial. So 1 over 2e. Right? And similarly, probability of finding 3 photons will be equal to 1 over 6e. 3 factorial. And so on. Right? So basically, what you are finding is, if you have the mean number of photons to be 1, you have initially some probability, but quickly it reduces. Okay. So like that, you can actually, in this picture here, I have shown the probability, the distribution that you will see when the average number of photons is different. The first case you are only having, let's say 0.1 photons here. So you see that quickly you will find most of the times you make a measurement, if you have a 0.1 photon, the case we have seen, right? What does it mean if you want average number of photons is 0.1? You make 10 measurements, most of the times you will see no photon. Only in one event you will see. So that is why if you make this measurement 0.1, you will see that the probability of finding a 0 number of photons is 90. 0.9. The probability of finding 1 photon is 10. 0.1. Right? So this is the distribution you will get. But the moment you go to 1 photon, you saw that 1 over E, and then quickly it reduces. 1 over, 2E, 1 over 6C, and, even smaller. Right? 3 into 2, 24, 1 over 24E and so on. It will quickly drop probability. And now if you go to, let's say, average number of photons is 5. This is a case where you are taking a larger line segment. Okay? That means the average number of photons in that segment is large. Right? So if you have such a scenario, you see that the average, there is a distribution that you see, and the center of the distribution is n bar. Okay? So basically these are all Poisson distributions, right? So these are basically distribution centered around n bar, right? It has two important parameters. One is n bar, which is basically the mean number of photons, and delta n, which is basically the fluctuation, right? Fluctuations in the number of photons. Okay, and Poisson distribution has a very characteristic feature that the fluctuation is going to be square root of average number. So that is a characteristic feature of a Poisson distribution. So delta n is going to be square root of n bar. Okay. So all the graphs here are plotted with that assumption. So basically, if you have average number of photons to be phi, what is the fluctuations? You will see square root of phi. Delta n is going to be square root of phi. So 2 point something. But if you have average number of photons to be 10, the fluctuation is going to be delta n is equal to square root of 10, which is going to be 3 point something. So what you are noticing is, if your n bar increases, right? So average number of photons increase, the absolute magnitude of fluctuation increases, right? So basically you will see that delta n increases as n bar increases. Okay, that is the one of the features. But there is another thing we can consider, which I'll call as relative fluctuations. That means delta n by n bar. How much is that? So delta n is my fluctuation, n bar is my, delta n by n bar is my mean number of photons. Okay. So it's not enough just to talk of the absolute fluctuations in the number of photons, but also relative to the mean number is what is interesting, right? So what you see is, if you take the case of 0.1 divided by n bar, how much is that? 0.1 square root of 0.1 is how much? 0.3 something, right? So here in this case it's going to be square root of 0.1 divided by 0.1. That's going to be 0.3 divided by 0.1. So roughly 3 something, approximately 3. Okay. In the first case. The second case is going to be 1 divided by 1. So the relative fluctuations is going to be 1 divided by 1. So 1. Okay. The third case, you have delta n is square root of phi. Square root of phi is 2 point something, 2.12 something divided by phi. So 0.5 something or 0.6, 0.4 something, right? And if you go to 10, average number 10, it will drop even more. 3 point something divided by 10, so go 0.3. So what you are seeing is the relative fluctuations delta n by n reduces as n bar increases. Sorry? As n bar increases.
The probability is more uniformly distributed.
More sharper, more well defined. The fluctuations are less. Relative fluctuations are less. So if you have 10 power 15 photons, I'm sorry. Okay. The case of 10 power 15 photons per, whatever. Average number of photons is 10 power 15. So you are measuring for 1 second. A 1 milliwatt laser beam and 10 power 15 photons in that. What is the fluctuations in the number of photons? Delta n. Square root of 10 power 15. 10 power 7. Right? 3 into 10 power 7 something. Right? So 3 into 10 power 7 relative to 10 power 15 is very, very tiny. In the 7th decimal, you are seeing some variation in the number of photons. You don't care. So when you have a large intensity beam, like this, let's say my laser beam, my laser pointer, which has 1 milliwatt of power, I don't have to worry about the quantum nature of the light. I don't have to worry because the fluctuations are very, very small. But the moment I come down to, let's say 1 picowatt beam, which has 1 nanowatt beam, what was the case we took last class we took, no? This one, sorry. If you take a 1 nanowatt beam and 30 centimeter segment, we had 3 photons. Average number of photons is 3. So square root of 3 is 1.7 something. The relative fluctuation is almost like 0.5. Significant when compared to the average number. So we'll have to worry about the quantum fluctuations. In the number of photons fluctuation, we have to take into account. We cannot ignore that. That's a message. Okay. So this is what is called as a Poisson distribution. This is the main message, right? That is why we are saying, always remember the first thing that I talked about here, no? In the first here, when I'm talking about quantum optics, I'm talking about lower intensities. I don't have to worry about the quantum nature when I'm in large intensity. Large intensity is going to be classical. It's enough to talk of plane waves and exponential, IKX sort of waves. You don't have to worry. The moment you come to small intensities, the quantum nature becomes significant. Okay. Any questions? Okay. All right. So let's try to do one problem. Again, the same thing I'm trying to do in multiple different ways. This is an example I've taken from Mark Fox. Example, in 5th chapter, you can go and look at it. This is the textbook reference is given in the bottom here. Okay. This is a quantum optics textbook. So the question is, an attenuated beam from an argon laser operating at 514 nanometers, it's corresponds to 2.41 eV, with a power of 0.1 picowatt is detected with a photon counting system of quantum efficiency something, with a time interval set to be something. Calculate the mean count value. Mean count, I guess, is basically how much is the number of photons detected at the detector, right, with the photon counting system. So first thing we have to look at it is what is the photon flux. So you are given power and you are given the energy of the photon. So photon flux, we have done this multiple times in the last lecture. So it's going to be 0.1 picowatts divided by, 0.1 into 10 power minus 12 divided by 2.41 into 1.6 into 10 power minus 19. Okay. No, I have a notes here which tells me what the answer is. It is going to be 2.65 into 10 power 5 photons per second. Alright. This is my calculation. Now, this is my photons incident on the detector, let's say, on the counting system. What will be the counts registered? Now, the interval is 0.1 seconds. Okay. Small intensity, but the interval is large, relatively large, 100 milliseconds, right? So the count rate R is going to be the photon flux phi into the time interval. But then we should remember that all the the detector's quantum efficiency comes into picture, and we would like the detector's quantum efficiency to be high, but sometimes it is not. In this case, the quantum efficiency is given as 20%. So this is going to be eta. Out of n number of photons, only eta times n will actually come out, will be detected by the photon counting system. So this is going to be equal to 0.2 into 5. Photon flux is 2.65 into 10 power 5 into time is 0.1. What will that turn out to be? So 0.1 into 0.1, so 2 tens will go off. So 2.6 into 2.65 into 2. Sorry, 2650, 5300. 5300 photons is what you will detect. Alright. The count rate is that much. Right? Flux is given to you. Flux you calculated. Once you have that much of photon flux, how many counts? Now what is the mean count now? Mean count is 5300 photons. So n bar is going to be 5300 as detected by the system. Photons per second. Photons, not photons per second. Alright. Standard deviation of the count. How much? You are assuming a Poisson distribution, and the standard deviation is simply going to be delta n square root of n bar. So that's going to be square root of 5300. That's going to be something approximately 7 into 7, 49. Yeah. 70, approximately 70. So if I look at the relative fluctuations, okay. That's going to be equal to 70 divided by delta n divided by n bar. That's going to be 70 divided by 5300. 1/7. 1 over 70 rather, right? This is quite small. Relative fluctuations are quite small or negligible. Okay, that's the thing. When you have a large photon number, the fluctuations are insignificant. We have 5300 photons, mean number of photons. For large n bar, the fluctuations are insignificant. And that is why you have to go to smaller time intervals where you actually see. Okay? So you might say, why are you worrying so much? Well, the interesting thing is here. Now we can classify the type of light sources based on the statistics they exhibit. Okay? The first type of light source is what we will call as Poissonian light source. Poissonian light. Basically that means that your delta n is equal to square root of n bar. What kind of light source will exhibit this? It will be a perfect. An example for this is going to be a perfectly coherent light beam. Remember, we considered constant intensity, perfectly monochromatic source. Still you will see some fluctuations. Okay. Now this is a a perfect laser essentially will exhibit Poissonian distribution in photon statistics. Now you can have another scenario which we'll call as super Poissonian. That means your delta n is going to be greater than square root of n bar. What sort of light sources will give you this super Poissonian? The fluctuation should be larger than the intrinsic fluctuations. One of the simplest forms is take a laser beam and modulate it. Change the intensity randomly. Of course, it will have more fluctuations than the perfect laser. Perfect laser is a monochromatic source, continuous wave. If I pulse it, let's say, or fluctuate, modulate the intensity, right? Or time varying light intensity. It can be time varying light or laser. We'll have super Poissonian statistics. A pulse is, still there is some order to it, right? But if I'm varying randomly in time or something like that. Okay. Well, if you take a pulse laser beam, in that particular window it is there, but the distribution is not going to be large. It depends on how let's say you are considering 1 kilohertz beam and your pulse is on for 100 picoseconds. You'll have that much and then fixed again that. There won't be randomness. Super Poissonian, generally one of the most popular examples is basically thermal light source. That means you heat up an object, it emits light. Take a piece of steel and heat it to 500 degrees. Okay. In the olden days, actually people used to look at the color of the metal and figure out what temperature it is. People who are skilled at it can figure out, is it hot enough or not to actually hammer it, right? Looking at it, they can figure it out because the light emitted will be different. The color variations we can find out. Okay. So thermal light source is one example, wherein basically you have random, the light is emitted incoherently and it's having random fluctuations and the wavelength also is broad and all that, right? So a thermal source is basically another example of a super Poissonian light or even an incoherent source. Incoherent light, whichever it is, wherever it is, broad emission is going to be super Poissonian. Okay. And the third class is basically going to be sub Poissonian. Okay. What do I mean by that? Well, I mean delta n is less than square root of n bar. And this is a situation where we don't have any classical analog. No classical light can exhibit sub-Poissonian statistics. So, demonstration of sub-Poissonian statistics is one of the signatures of quantum light. You are having a quantum light source. Lesser than the Poissonian. If your delta n given by Poissonian, if you have an average count of 1, you should get maximum of square root of 1. If you get to that point, then you can say that you can claim that you have a quantum light source. Okay? I mean, if you look at the distribution, it's obvious already. We saw that the distribution right here. In this case, if you have a distribution like this, the center is basically this, the width of that distribution is the fluctuations, right? Delta n roughly. So you can see that if you have a sub-Poissonian light source, you will have a very, very sharp output, right? This is sub-Poissonian here because the width is very small, delta. So Poissonian is this solid line. Super Poisson is broader than the Poissonian statistic. Sub-Poissonian is sharper than that for the same average photon number. All three graphs here have the same average photon number of 100. Okay. So if you have a sub-Poissonian light, distribution is narrower. In this case, distribution is broader. Okay. So that's how you can classify light sources. You might say, why should I classify light sources? Well, the idea is that you can get to study the properties. Okay, we'll study the properties in greater detail in the next few weeks. Okay. So let me also show you how, let's say, thermal light varies from a laser. Okay. We have talked about the black body distribution, wherein we said that this is my density of states and this is my average energy per photon, and this is, average energy per mode. Average energy per mode. So it turns out that the Poissonian distribution we have seen already. Okay, wherein let's say you have in this case average photon count of 10, you will have distribution breadth, something given as, right? But if you have a thermal light source, especially if thermal light source is emitting into a single mode, it follows Bose-Einstein distribution. Okay, so the probability of such a source will be different. The probability of finding an n electrons in this case will be different. In this case, it will simply be n bar plus 1 and n bar by n bar plus 1. To the power of n. So it follows what is known as Bose-Einstein distribution, which is given by the expression here. So quickly you see that what is the probability of finding, let's say, n photons, right? So we can quickly see again the same thing we can repeat. So probability of finding 0 photons is going to be 1 over 11, right? N bar, so sorry, whole thing to the power of 0. So probability of finding 1 photon is going to be 1 over 11 into 10 by 11. Probability of finding 2 photons is going to be 1 over 11 into 10 power by 2 square and so on. So basically what you will see is this expression here, this graph here, wherein the number of photons, the probability reduces. At 0 photons you have the maximum intensity. And that is also kind of makes sense because in Bose-Einstein statistics, you have, let's say, a distribution of photons. In Bose-Einstein, bosons tend to occupy the lowest energy levels. The probability of finding photons at the higher energy level, bosons at the higher energy levels is small. So that's why you see that 0 photons will have the maximum probability and it reduces quickly. Okay. And I mean, that is also obvious because, this is my, if you look at this expression closely, I said 1 over this particular term is my number of photons. As you can compute at different temperatures what it is, and as the number of photons increases, this should reduce. Okay, the whole thing will reduce. So the probability reduces. Anyway, so now if you look at it, it's very obvious that if you take a Poissonian case, delta n. So okay, I should maybe just make a note here saying that thermal light follows Bose-Einstein statistics, not Poissonian. It was actually, Satyendranath Bose who studied this, and then he wrote a paper he sent a letter to Einstein, and then they collaborated and finally came up with this. So there was a time when we used to do great science. Anyway, so so this is the distribution that is given by, the probability of distribution is that. So now you will see that, why is it not? If you have a Poissonian statistics, delta n is going to be square root of n bar. This is Poissonian. Immediately we are seeing that thermal light source, the delta n is larger. So for a thermal light source, or rather I'll actually write it in a different form so that it is, instead of writing the standard deviation, I'll write the variance. Variance is simply standard deviation square. So that is going to be n bar for a Poissonian statistic. For a thermal radiation, black body radiation, delta n square is going to be n bar plus n bar square. Okay. For a single mode radiation, this is how it is. We are not proving it. I'm just mentioning that. That's it. Okay. So this is thermal radiations in a single mode. But it turns out that, we talked about the number of modes. Omega square by pi square c cube. Omega square is 10 power 14 into 10 power 14. So 10 power 28 divided by c cube will be 24. 10 power 4. So there are a large number of modes. Right. When you have large, it's very, very rare to actually have thermal radiation emitted into a single mode. When you have large number of modes, this expression is actually modified for large number of modes. Delta n square equal to n bar plus n bar square divided by number of modes. When the number of modes increases, effectively the thermal light source also starts to behave like a super Poissonian source. If you have a single mode, this Bose-Einstein statistics will come into picture. But as nm, number of modes increases, thermal light source exhibits super Poissonian statistic. Okay, in this, I would say that, don't worry too much about it, because it's a little bit of detail, but because it's different, it will be useful to know. That's why I'm mentioning. It's okay if you don't fully understand this aspect, but I hope the Poissonian part is clear. Why the super Poissonian is, let's say thermal light source is a little bit of an additional thing. It's okay. We can, right now I would say that, okay, you just take it as it is. Okay. Where variance is basically n, mean number of photons is equal to the variance for a Poissonian distribution. But for a super Poissonian thermal light, it is basically average plus average square. There are two terms. The second term sort of goes to smaller values as the number of modes increases. That's it. Okay. Just is a bit of information maybe you just can keep in mind at the back of your mind. All right. So this is about thermal radiation and comparison with the Poissonian case. What about the sub-Poissonian case? This is a very exciting thing. So now, how do we get a sub-Poissonian source? We should have delta n less than square root of n bar, right? Or not less, less than, right? Now we said a perfectly coherent laser has delta n equal to square root of n bar. How do we actually go sub-Poissonian? What does it mean delta n is less? What is an ultimately, perfect sub-Poissonian source? Where the delta n is 0. Okay. So if I have my delta n equal to 0, that implies a perfect sub-Poissonian source. What is such a source? Delta n is, so you have basically, if you think of a stream of photons, like in this case, so he's showing you a beam segment, let's say something of some length, the distribution of photons is perfect. Okay, that means each photon occurs at the perfect precise time. There is no fluctuation. When you have no fluctuations at all, then of course delta n is going to be 0. Right? If you consider a scenario like this, a perfect source is one where you have no fluctuations in photon arrival time. Okay. How do we, and if you look at the distribution is going to be like this, wherein you have average number of photons, and that is where the probability of finding the average number of photons is 1. You compare this with a Poissonian source. Even if you take like n bar of 10, right? The probability is only 0.1 to 0.13 or something like that. So even though the average number of photons is, let's say 10, there's only 0.13 probability of finding it when you make a measurement. But if you have a perfectly sub-Poissonian source, if you make a measurement, you will always find n bar, average number of photons. Okay? And this has a lot of crucial importance because, slowly we are talking about quantum regime, right? Quantum computing and so on, quantum key distribution, quantum communications and so on. In that, it's very important for us to generate a single photon. Okay. One of the important, if you look at any of the recent literature, you will see that a single photon source is something very, very important, and a lot of people are trying to do this. Single photons source. Okay. What does a single photon source do? It generates a single photon on receiving a trigger. Okay. An example could be, if you have a two-level system, right? We studied two-level system. Let's say there's an electron in the excited state. On receiving a trigger, it basically emits a photon. Okay. It de-excites and emits a photon on receiving a trigger. Okay, that's a single photon source. So basically, you make sure that you have the excited state and then simply make it emit a photon. Now, will it really be deterministic? Because if it's emitting a photon, that's going to have spontaneous emission. There's a certain lifetime associated with it. Let's say I send a trigger at, with a frequency of 1 megahertz. 1 second, 1 microsecond, 2 microseconds, 3 microseconds, and so on, I trigger. But will it emit a photon exactly at 1 microsecond? No, there's going to be some gap. But provided my radiative lifetime is very, very short, I can emit close to that. If my radiative lifetime was 100 nanoseconds, so every time I send a trigger at 1 microsecond, in the next 100 nanoseconds, it will emit a photon. Again, next microsecond, second microsecond, it will emit a photon in the next 100 nanoseconds. But if I can reduce the radiative lifetime, 1 microsecond, within 100 picoseconds, it will emit a photon. Second, 2 microseconds trigger, it will emit immediately. 3 microsecond, it will emit a photon. Do you know how to reduce the lifetime? Purcell factor. So basically, you create a nanostructure which has a very large density of states. Then the spontaneous emission lifetime reduces. So nanophotonics can be used to generate deterministically. Okay, But is it possible to create exactly one electron excited in the high level? No, you're going to excite more. Then you'll have more than one photon emitted, but all within that lifetime, of course. And now you attenuate it and get a single photon if you need. Okay? So that's one of the crucial technologies that people are looking at right now. Okay? So this is an important feature of sub-Bosonian light. All right? Any questions? All right. If not, let us stop here. Thank you so much for your attention. I'll see you in the next lecture. Take care.